All right, guys, so I'm going to go over the notes for topic 6. So I want you guys to follow along in your notebooks while I do this. So the first thing you see here is a graph that shows how a reaction and the progress over time and what happens to each substance as the reaction progresses. So as far as the rate goes, so this is what we're looking at. We're looking at reaction rates. So what you can see here is that NO2 is the reactant, right? That's the green line. And basically as the reaction progresses, the line decreases because the reactants are being used up as the products form. So the products are NO and O2. NO is the blue line and O2 is the red line. Those are both increasing because as the reaction progresses, the products are being formed, so those increase. You can see that the blue line is higher than the red line because notice the coefficient in front of NO is 2 and the coefficient in front of O2 is 1. So the NO concentration is increasing faster than the O2 concentration. And that's a multimole ratio. You can determine that by looking at the multimole ratio. So along the side, it talks about how with reaction rates, you can measure the disappearance of the reactants, aka the green line. And you can measure the appearance of the products, again, the blue and the red line. And they are proportional stoichiometrically. So that's why you see the red and the blue line, the difference there. Because the blue line, the NO is forming twice as fast as the O2. So a little bit of a review about reaction rates. So for a chemical reaction, the reaction rate is the change in concentration of a substance per unit time. So you see here the delta concentration, change in concentration divided by the change in time. The units that you're going to be working with in IB are going to be moles per decimeter cubed, that's the concentration, per second. So those are the units of rates. And all of this goes back to collision theory. So if you guys remember this, we went over collision theory last year in sophomore year. The collision theory states that atoms, ions, and molecules must collide in order to react, but they must also collide in the correct orientation and with sufficient energy. So if you guys remember when we discussed the collision theory last year, those 3 things have to happen. So they have to collide, number 1. They have to collide in the correct orientation, so they have to line up correctly. And the third thing is that they have to have enough energy when they do collide. And so during a chemical reaction, many collisions occur, but they don't always produce a reaction because sometimes atoms or molecules, they collide, but they're not lined up correctly, or they barely bump each other. They don't really have enough energy to form a reaction. So they don't always, only some of the collisions produce a reaction. But when they do collide with the correct orientation and enough energy, then that's when they form the activated complex. Remember when we drew the exo and endothermic graphs? The activated complex is what's formed and lives temporarily in the transition state. It's a very temporary and unstable arrangement of atoms that break apart into the products. So again, when they do form that activated complex, it's at the very top of the hill. Remember the activation energy hill? And that's called the transition state. So the top of the hill is called the transition state. And in order to get there, the energy, the amount of energy required for those reactants to get to the transition state is called the activation energy. And that is going to be represented with capital E and then a little subscript A, activation energy. So here's your 2 graphs. This is all review from last year, and so hopefully these look familiar to you. We have the exothermic graph on the right and the endothermic graph on the left. So you know that this is endothermic because the energy of the products are at a higher level than the energy where the reactants started. And so this amount of energy to get to the top of the hill is called the activation energy. And then when the products form, it goes back down. And if they end up at a higher energy, then that means that in this particular reaction, energy was absorbed, and so it's endothermic. In this one, so here's the energy of the reactants, the amount of energy to get to the top of the hill, again, activation energy. This time when the products form, they end up at a lower energy than the reactants. That means that this amount of energy was released, and that is the exothermic process. So when you do your IA, you're going to be looking at some different independent variables. You're going to be changing something 5 times for your IA. And so some of the independent variables can be surface area. In other words, you could do reactions with substances of different surface areas. In other words, something that's finely broken down, something that's in bigger pieces, something that's in big chunks. You can look at the various surface areas. You can change the concentration. You can use something that is low concentration, medium concentration, high concentration. So you can change the concentration of something 5 times. You can do a reaction in 5 different temperatures. You could do one at room temperature, one in an ice bath, one in boiling water, and then you can also use different temperature water baths to get 5 different temperatures. You could also potentially use different catalysts to see how that affects the reaction rate. What would you be measuring? What would be the dependent variables that you would potentially observe? You could be measuring the amount of gas or pressure that's being released. You can be measuring the mass, how the mass of the products change. You could potentially do color, but that would only be qualitative data, not quantitative, and you have to have some quantitative data to perform calculations. So that could be something that you're observing, but there also has to be some kind of quantitative data. Change in pH, you can measure pHs, and you can also do changes in conductivity using a conductivity probe. So any of these are different dependent variables that you might be measuring. So changes in concentration can be followed indirectly by monitoring changes in mass, initial and final mass. So you could subtract to find out how much mass was lost. Volume, gas collection. We do have probes for gas collection, and we do have spectrophotometers as well to if you're doing observations of color. Okay. Next section, factors affecting reaction rates. So there are 5 factors affecting reaction rates. Again, this is all review from last year. Number 1, nature of reactants. Some reactants are more reactive than others simply by the location of the elements on the periodic table. For example, Na is much more reactive than Ca only because it's in group 1 and it only has that 1 valence electron to easily lose, whereas calcium has 2 valence electrons. So it's not going to be as reactive because it has to use more energy to lose the 2 valence electrons. So again, that's a little bit of review from atomic structure, and that's a little bit of review from topic 3, periodicity, periodic trends, where we found out that group 1 is going to be the most reactive, and then group 2, and then group 3, etc. So reactivity, we talked about that in topic 3. Number 2, the second factor that affects reaction rates is concentration. So if you have more substance in the reactant, so basically more reactants that you add to a reaction, the more the reaction will take place because there are more particles to collide. It's like being in a crowded area. More people are going to provide more reactions, more collisions. The third one is surface area. The smaller the pieces, the more surface area to collide with other particles. So again, if you have big clumps of sugar, it's going to take longer to dissolve. Whereas if you break it into smaller pieces, it's going to dissolve faster. And that's because you're increasing the surface area when you break it into smaller pieces. Number 4 is temperature. Generally, increasing the temperature is going to increase the kinetic energy of the particles, which is going to increase the frequency of collisions. So anytime that you're asked a question about how temperature affects reaction rates, you have to talk about how it makes the kinetic energy increase. Remember, kinetic energy is the energy of movement. And so as a result, there is going to be more frequent collisions because the particles are moving more. And number 5, adding a catalyst. So there are times where you are going to want to increase the reaction rate. You're going to want something to go faster, but you can't necessarily increase the temperature, because if you're increasing the temperature, say in a living organism, like a living cell, it's going to burn it and it's going to kill it. So instead, we use catalysts to increase the rate of a reaction without causing harm to any of the substances. So remember that a catalyst is going to increase the reaction rate without itself undergoing the chemical change. So the catalyst is going to be there at the beginning of the reaction and at the end. And it's not going to be a part of the reaction, but for whatever reason, it has this property where it it helps the reaction go faster, but it doesn't actually participate in the reaction. It does provide, what it does is that it provides an alternate mechanism for the reaction, and that other mechanism has a lower activation energy. So again, it doesn't make it go faster by speeding up by lowering the activation energy. It provides a different route, like a shortcut to get to the other side of the activation energy hill faster. So just notice I wrote here in green, be careful not to say that it lowers the activation of the energy of the reaction. Instead, it provides this part right here. It provides an alternate mechanism, a shortcut for the reaction, which has a lower activation energy. So here's a diagram showing how a catalyst affects it. So the blue line is without a catalyst. Notice it would take a lot more energy. Adding a catalyst gives it a different route, a shortcut to get to the other side. All right, guys, this is a new material. This is not review. This is brand new. The Maxwell-Boltzmann energy distribution curve. Okay, so I want you guys to notice the lines. The one here at the top is at 0 degrees Celsius. That's a cold temperature. The one at 25 degrees Celsius, that would be room temperature. And then 100 degrees Celsius is like boiling, the boiling point of water. So it's hot. So as the temperature increases, so does the probability of the molecules having higher energy. It also increases, which means that there's going to be more particles that are potentially going to be involved in the reaction. So look, the blue, under the blue curve, that's when it's cold. The particles aren't moving very much when it's cold. So there's not very many particles that are going to participate in the reaction because they don't have enough kinetic energy. If you have a reaction that happens at room temperature, 25, that is what's under the green curve, the green color, and the blue. All of these particles, green and blue. So now you have more particles that are going to have enough kinetic energy and potentially undergo the chemical reaction. And then as the temperature increases to 100 degrees, notice that is under the yellow. So you've got the yellow, the green, and the blue. This entire area now is representing all the particles that will form that will have enough kinetic energy to form a chemical reaction. So the probability increases with higher temperatures. Here is another example of that. And this is an example of a diagram you would have to draw on your IB test. T1 is a lower temperature, and T2 is a higher temperature. See right here, it says T2 is greater than T1. The second temperature is higher than the first temperature. Notice that under the T1, the colder temperature, you got the red lines, the red stripes. That's a smaller area than when you have a higher temperature. And now it includes all the blue and the red, a much larger area with with particles that have kinetic energy that will form a reaction. Whenever you are given data, you're going to be they're going to ask you to analyze graphical and numerical data. So you would see a graph like this, and you would basically do the slope formula. You would just take the 2 points and find the slope of that line. To find the tangent at a certain point, take the change in concentration, change in y, divided by the change in time, change in x. So again, the slope formula, change in y over change in x. And you just need 2 points for that. You just pick 2 points for the graph. Rates of reaction are always expressed as positive numbers, even if the slope is negative. The rate at the beginning of the reaction is going to be the fastest, because as soon as the reaction starts, that's when there's the most particles to react. So it's going to be really fast, and then it's going to slow down towards the end. The rate at the end of the reaction is the slowest. The average rate of reaction can be calculated by finding the slope with the first and last point.